Okay, so we left off, I believe, we'd started kind of talking about weighted means and kind of the process for which we calculated a weighted mean. So we had, we had this formula which said we're going to have some variable, but we only have group data, right? So we can see group averages, and we can see the number that were in those groups. So if we use that number in the group as our weights, we use the value we see for each group as the variable x, we multiply the weights by each one of those groups' value for the variable x we're interested in, add them all up, and then divide by the sum of our weights. Right? I think we walked through kind of this first example, finding the male kind of weighted mean for the males here. And then I think what we left off was, if I remember right, kind of asked this question of if we had something like this, which one of these regions would influence that weighted mean the most? Well, it's going to be the one that has the largest, right? So here's a good way. If I just like, make sure everything's good here. Okay, cool. If I take these mean incomes, we found that weighted mean was 53,000. And I'll use this for right now. Just use a blank sheet. I'm going to paste those in here, blow it up so we can see it. If I was to just find the mean, the normal way of these, I'm going to get about 48,000. Now, why did we find 53,000? Why was it so much higher when we appropriately used the weights because it was kind of group data? Well, because notice the value that's going to have the most influence here was 59,000, because this group, right, is about what, a little less than 70% of all the observations, right? It represents about 70%. And so its weight is going to be much, much higher. So that 59,000 is going to pull that mean up much higher than these lower values of 38 and 36, because those are very small groups relative, right? Their weights are relatively small compared to that large group, right? So whatever has a higher weight, that's going to influence what we end up seeing for the weighted mean the most, right? So instead of getting 48,000, this observation, this group that has kind of a high frequency, high weight, pulls that mean all the way up to 53,000, okay? So if we look at these regions, kind of which one would be the most, we said, I believe it was the south, right? Because it's got the highest kind of frequency, the highest weight there. So I think that was kind of where we left off, right? So we had a little bit of introduction of these weighted means. Well, if we can do weighted means, we can probably also do weighted variances, right? So I've got the weighted variance equation. It's going to look very, this mouse is sensitive, very similar to what we were doing for the variance, but we're just going to add the weights in to that numerator, right? So I'm still going to look at the variable I'm interested in, x. I'm still going to subtract the mean from that. I'm also still going to square that deviation. But then I have one additional step, was once I find that square deviation, now I multiply it by the weight of whatever group I'm looking at, okay? So I do that for every single observation. I add them all up. When I say every single observation, every single group here, because we're dealing with group data, we have to find a weighted variance. I'm then going to divide by the total number of observations. So I wrote n here, but really, if I think about it and I go back, the original data, right, that I can't see, like before it was grouped, the number of observations in it would just be, right, every observation would belong to one of these groups. So when I add up the weights, I'm actually going to get the total number of observations in the original data before it was grouped. So anytime I see the sum of the weights, I can really also think about that as n, right? So if I'm looking at that equation for the variance, I could write the sum of the weights in there as the denominator as well, right? That'd be the same thing, okay? So what's that going to look like? So I kind of put the values in here, but I'll kind of walk through this and then kind of show you in Excel another way we could think about this, or how you could work through it in Excel if you wanted to, I guess. So the very first thing we're going to do is go to that very first group. We're looking for the variance in income, so we'll take that group's income, subtract the mean, Now the mean was at 53,000 we found a couple slides prior. So 59,000 minus 53,000, square that value. Once you square that value, then multiply it by the weight for that group, which was the 73,000. If I do that and write that number down, I get what? 2 million, billion, I don't even remember what's above a billion. Or a trillion, yeah, a trillion, right? So we're looking at this. We can do this for every single group, right? Now notice the groups that, it's a little bit different than the variance before. So now an observation or a group here is going to influence the variance if it's really far from the mean. So the weighted mean here is 53,000. So it'll add a lot to the numerator of that variance if it's really far from 50,000, but it also adds more if it has a higher weight. So notice this value, this group has a value very far from the mean. It's 7,000 away from 53,000, but the weight is much smaller, right? So this is a little bit closer to the mean, but because the weight is so much larger, notice this is 2 trillion and this is what, 316 billion, right? So it's quite a bit larger because it has a higher weight, even though they're both pretty far from the mean there, right? So now we have two factors influencing kind of how much gets added into the variance. Okay, so if we do that and then add these up and divide by the sum of our weights, we should get 94,000. But I'll show you kind of another way to do this in Excel. I'm gonna get a little bit of practice thinking about Excel. So all I'm gonna do here, I'm working. Oh, let me make sure I grab the right, where was it? Right here. So I'm just gonna, nope, that's not what I'm gonna do. Let's grab the data here, copy it, go to Excel, paste it down here somewhere, get rid of the old work that we did. And I'll actually even get rid of these so I can show you how we do it, right? So the first thing we have is we want to take the weights times x minus the mean squared. Right? So these are our weights. And this was that income variable that we were interested in. Right? So all I have to do, and I can do this in a calculator, right? And there I'd have to type out the numbers, or I can do it in Excel, and every time I want, a certain thing, I can just click on where that number is at. So what I want to do is I want to take the weight of this group. I'm going to multiply that by the value for the variable x minus, I'm going to click on this cell up here, and I'm going to put the mean there. I forgot to do that ahead of time, but it's okay. I can reference the cell, and then whatever I put in the cell, it'll use. So I'll reference this cell, E5. I'll put the mean there. So it'll take the value x, subtract the mean, square it, and then multiply it by the weight. So if we go up here, what was it, 53,000, let's get it exact here, 296, okay? So 53,296, right? Sure enough, it gives me that value that I see in the slot, right? So that's all I'm doing. I'm basically using that formula for each observation. Now I could type this in again and write in a calculator, I'm gonna have to, or if I'm in Excel, I could copy this down, but if I copy this down, what's gonna be the problem? These values don't actually match up with what you have in the slides. Why? Yeah, right? It's using nothing from E6, so it's subtracting 0 from that value. So what I need to make sure is I'm always subtracting the mean. So I'm going to put my dollar signs in front of that so that this cell reference doesn't change when I copy it down. And now I should get those values that I saw in the slides, right? Now, once I get to this step, I have to add up, right? That was that sum of the weights times x minus the mean squared. So add all these up. And then I could say, well, if I really wanted to, I could do all this in one cell. Once I add those up, what do I need to divide by? We said we divide by n, or n kind of representing the sum of those weights, right? So in the same cell, I can also put in, divide it by the sum of just the weights. Okay? And that should give me that 94, I think it's a billion? Yeah, 94 billion. Or not billion, million, sorry, 94 million. Okay? So that's how you could do it in Excel. You could do all that same stuff in a calculator. You're just gonna be typing the numbers in instead of clicking on the cells that have the number, and it's gonna be a little bit more work, right? But either way, we'll get the same answer, okay? And if I'm doing it on a calculator, I think it for sure helps. It might help if, like I said, it's similar to last class. If you don't have a great calculator, it helps to write out the intermediate steps, your intermediate values. If you got like a TA 83, 84, you could probably type all of it in on one line, hit enter, and you'll be okay. Okay? All right, so we've got our weighted variance here. There we go. So if you wanted to, you could recreate what I just did. You could do it for females as well, right? You would have different weights, different values for X, but you could go through, find the weighted mean. In fact, the weighted mean is in a previous slide right here. You could then take the very first group, 34,000 minus the mean for, I think it was 32,000 or something from the previous slide. Square it, multiply it by the frequency for that group. Do that for every single group, add them up, and then divide by the sum of the weights again, right? So it might be some good practice. Like I just walked through in Excel and walked through with the pointing my mouse exactly how we would find that weighted variance for males here, but you could recreate the same thing for females and make sure that you could solve and find that 15 million as well, okay? Any questions on that before we keep moving here? Okay with that? I'm sure there's nothing in the chat. Okay. So notice females here, right? If we just look at the data, I think it's kind of easy to see there's less variation. Even if we just use that statistic of the range, right? It goes from what, 24 to 39,000, right? So about 15,000. Whereas if I look at the range for male income, 36 to 60, so 24 million. So even just looking at the range, it looks like there's a higher variation in the data. And we kind of see that with the variance as well, right? Once we calculate that variance, there's much less variation across the different racial groups in the female income than there is in male income, okay? And, kind of this shows somewhat, the gender and racial disparities in income values in the US, okay? One thing I wanted to mention here, it's not in the slides and it's just something good to know. Once we calculate the weighted variance and we calculate the weighted mean, they have similar properties. So if I wanted the weighted standard deviation, what's all I have to do to get, if I have the weighted variance, I can get the weighted standard deviation by simply taking the square root. It's just like it's just like a regular variance. I can just take the square root to get the standard deviation. So the same rule applies if you're doing a weighted variance. You can get the weighted standard deviation by just taking the square root there, okay? I kind of recreated it for median income. I won't spend too much time here, but you can kind of see, this also gives us a nice idea. When I broke this down by region, these values were much more similar. The average income across regions were more similar than when we looked at different racial groups. And notice these variances are much lower than when we were breaking it down by race because there was just more variation in the group data than this group data, right? So this variance tells us there's a lot less variation across regions in income than there is across different racial categories, okay? So once we have these variances, and especially when they're the same units, we can kind of compare across data sets, right? These are all income data sets, so we can look at the variation across region of the country or race. We could look at age groups is another one you can pull from the census. So once we have the same kind of starting variable, we can start to see where the most variation, say, in income was in the US. All right, so if there's no questions there, we're going to kind of start in something that's very similar. It's still like a weighted mean and a weighted variance. The notation is going to look a little bit different, and there's a couple caveats to it, but it's really the same principles. Okay? So let's say I have group data, right? I can't see the original data, but the original data was individual satisfaction rankings. So they could rank the product from 36 to 50, right? And I think it ends up being there was 65 observations. But for whatever reason, the way you are presented or the way you are receiving the data, you don't get that original response for each individual. All you get is there was 4 people that responded with either a 36, a 37, or a 38, or anywhere between these. There are 15 people who responded with a rating between 39, 40, or 41, so on and so forth. Right? So you don't, here, the frequencies are going to be your weights, but before, we actually had a variable x that took on certain values, right? Now, our variable that we're interested in finding the weighted mean of, the satisfaction ranking, doesn't have one value, it has these like bin ranges, right? So you can kind of almost imagine what we did when Excel, we talked about forcing continuous data into bins to get a histogram. It's almost as if all you are given is those columns that had the frequencies and the value ranges for your histogram. You don't actually get the original data, right? Well, if that's the case, it's going to be very similar to what we did before. So I'll come back here and we'll think about what the mean in a second. But that mean, right, and we're going to treat this as kind of a sample mean because it's just sample data here, which is not every single person. It's just 65 people that responded who used the product. We're going to use frequencies instead of weights, but really that's just semantics, right? I mean, but before our weights, really we're also representing frequencies in those categories as well. So, you know, it could be that if we weren't looking at one of these bin problems, instead of income before, we could have been doing something like, not the number of people in a group, but we could have been doing something like the amount of money I invested in a stock. And so there, the weights aren't always frequencies, but when we have this data that's been forced in these bins, it's always going to be frequencies. And so that's why instead of W here, we're writing F, because we know if we're dealing with that bin data, the range of values data, it's always going to be having a frequency that is the weight. We'll then use the midpoint, right? It's pretty easy, right? So it's like, it wasn't one value in this range. It could be 36, 37, 38. So what are we going to use as the value? Well, there was 4 that we'll say was the midpoint of this category, or 37, right? And for this category, it would be the midpoint is 40, 43, 46, and 49. So those midpoints will be the values we use, and now our weights will just be the frequencies. But once we get that, it's the exact same process. Multiply the frequencies by the midpoints for every single group, add them all up, and then divide by the sum of the frequencies. Or we could write it a little bit differently, which remember the sum of the frequencies would just be the total number of observations from that original sample data that we can't see, right? The original sample data that was used to create these bins and these frequencies, okay? Any questions on that before we keep moving? It's really similar to the weighted mean stuff that we were doing. So if we go back here, what would you say about the mean is going to be? Well, which of these categories are going to kind of influence the mean the most? The one that has the highest frequency. So this one, the midpoint is 43, so that's what's going to influence the mean the most. You then have on either side your next most common categories, midpoints of 40 and 46, which are both equidistant to 43, right? In the middle, in the most frequent category. So if I had to guess here, probably somewhere around 43, 44, somewhere in that range, right? Now, what can I say about the variance? Probably not a whole lot. I know it's going to be a lot smaller than the income data we were working with, right? Because the values are just a lot closer together. But in terms of like guessing exactly what the variance is going to be, we probably can't do that, right? But we can go through and calculate that variance. And once again, very similar to the weighted variance formula. It's just now our weights are frequencies. The values for X, we're going to be using those midpoints. And here, instead of the population mean, we've got a sample mean, since this is sample data. And instead of dividing by the total number of observations, like kind of, if we go back, instead of dividing by the total number of observations or the sum of the weights here, we're going to be dividing by the total number of observations minus 1, which we could also write as what? Remember right up here, I said you can think of the sum of the frequencies as being that n, the number in the data set that you can't observe. So n minus 1 we could rewrite as the sum of the frequencies minus 1. Okay? The sum of the frequencies in n are essentially the same thing here. Okay? So if I want to do that for this, right? Here I want to find the sample mean. I'm going to use that formula. I'm going to go through each group, use that midpoint, 37, times a frequency of 4, write that number down. Take the midpoint of this group, 40, times that group's frequency. So 40 times 15 is 600, write that number down. Do that for every single observation. Once I have that done, I'll add up all those values, all those products. That's my numerator, the sum of the frequencies times the midpoints. I then divide by n, or the sum of the frequencies. So I go to my frequencies, I add these up, I get 65. 2,795 divided by 65 gives me exactly 43. So instead of be around 43, it just so happened to work out it's exactly 43. Yeah?
I thought we were supposed to do n minus 1.
So n minus 1, the only time we divide by n minus 1 is for the sample variance. Remember, means, it doesn't matter if it's a population or sample mean, you always just divide by capital N or lowercase n. Yep. But it's the sample variance. Sorry, I was talking about the mean, the variance. Now I went back to calculating the mean, and then we'll calculate the variance. So we'll divide by n minus 1 when we do find the variance. So here, this was just the process, right, for finding the mean. It's a good question, though. So that's why we don't divide by n minus 1. If we want to find the variance, well, now it's in the numerator. Now we take the midpoint of that group, so 37, subtract the mean, which we just found was 43. So 37 minus 43, 37 minus 43, so what, -6. Square that, so 36. Multiply by the frequency, 4 times 36 gives you 144. Go to the next group, take its midpoint, 40 minus that mean of 43, so -3 squared, 9, times its frequency, 9 times 15, 135. Notice for this category, the midpoint is 43, but that's also the mean, so when I subtract 43 from 43, it's going to be 0, 0 squared is 0, 0 times any frequency is 0, and that adds 0 to the numerator of the variance because that group, right, is like an observation that is exactly the mean. So it shows no evidence that there's any variation in the data set. These other groups show or are evidence that there is some variation, but this one kind of observation, group observation, is not, right? It's not evidence that there's any variation. So once we do that, we go through every single kind of bin here, every group. We'll add them all up. The final step here is you divide by n minus 1, or the sum of the frequencies minus 1. So, oops, 65 minus 1 here. Yep. And then if I wanted the standard deviation, the only other thing I'd have to do is one more step, take the square root. Yep. So that should be easy enough. I mean, it's very similar to what we were doing with the weighted variance. It's just we use the midpoints. Really is the only difference there. Okay. Any questions on this before we keep moving forward here a little bit? Okay with this? Okay. Make sure there's nothing up here in the chat. All right. Okay. So the next thing we'll talk about is we've got these. Might have heard people talk about like percentiles, right? So the 75th, so P here is like whatever percentile we choose. So it'll be like the 75th percentile, the 90th, the 99th, whatever percentile that we want. So whatever that percentile is, what that's essentially saying is the 75th percentile would be such that it is higher than 75% of the other data, right? If you're in the 99th percentile, that means that you have a test score better than 99% of the other test scores. So whatever p-value you choose, right, for whatever your cutoff is, whatever percent you choose, you're saying that it's better than that amount of, or not, I shouldn't say better than, I'm thinking about test scores. It's higher than or greater than that percent of all the other observations, right? Or you can kind of think about, I can say it differently. If I choose the 75th percentile, right, that's saying that I am lower than 25% of the observations, right? So if I choose the 75th percentile, other observations, 75% of them are less than whatever value I have on the test. If I choose the 75th percentile or the 75th percentile, my test score would be worse than 25% of the observations, right? Or 100 minus 75 of the observations, okay? I mean, I think I'm using test score as an example. You could look for the percentile for anything, but I think just with like SATs, ACTs, other tests you might have taken, you've probably heard this terminology to a degree. How many of you took the ACT and SAT? Probably all of you, okay. Well, yeah, I know that they don't require you to take anymore. At least Ball State doesn't require so. But they probably told you what percentile you were in, right, of those different scores that you got. So, or you've like seen something like this. I always thought this was like a crazy chart, like, because you've got so many different dimensions, right? So they put these different percentiles, 5, 10, 25, at different ages for different heights, to kind of see like, if I'm 14 and I'm only, 60 inches tall, I'm in the like 10th percentile height, meaning that there's only 10% of people shorter than me at that age group. And 90% of people would be taller than me at the age group, which I think is probably, no, I was definitely shorter than that when I was 14. Anyways, but yeah, if you've seen something like this, you can graph percentiles, kind of a fun little thing. So how do we do that? So the first kind of step is, if I'm saying that I'm better than 75, sorry, even better. If I'm saying that have a value larger than 75% of the other data, the first thing I'll have to do is arrange the data from smallest to largest, okay? So maybe I'm interested in finding what test score is the 75th percentile. Like what test score would be exactly above 75%? Now, 1 percentile would be really easy to find, and we actually already know the method for finding that. What percentile would that be? What's a statistic that we came up with that would actually represent a certain percentile here? What was the definition of the median? It split the data in half. It was above 50% of the data, below 50%. So it is the 50th percentile, right? But for any other, value, anything other than 50, we'd have to use a different approach. So we'll go from smallest to largest, arrange them in kind of ascending order. Locate the position of the percentile first. So for instance, if I had 100 people and I wanted the 75th percentile, it'd be easier because I can go to that 75th highest observation. But what if I want the 75th percentile and all I have is like, or I have, 364 observations? Well, then the position isn't as clear, right? And so the way that you're going to find the position is kind of using this formula. And actually what I told you is not completely correct. So if I have 100 observations, the 75th percentile, I actually would need a value slightly higher, which is kind of where this n+1 comes into play, right? Because if I choose exactly that value, it's going to be like, have just under 75% of it because I'm choosing that exact value. That value, it wouldn't be greater than that, right? So the equality kind of matters. So we would choose something that's slightly above it to make sure we're capturing whatever was in that 75th position. So this formula will give us the position in whatever data set we have, regardless of the number of observations, right? Whether we have 100 or 364, whatever number I used before. So you'll take the number of observations you have, add 1 to it, multiply it by whatever percentile you want over 100. That gives you the position. If this position ends up being an integer, we got lucky. If it's exactly 284, we go to the 284th highest value. That's my 75th percentile. If it ends up being not an integer, I'm going to have to do something called interpolation. All right, and I'll try to give you an idea about what this is here just in a second. But really all it is finding a middle value. So if I'm in, let's say I had the position was 3.4. Well, then I know that the value that's the 75th percentile is somewhere in between the value that's in the third position and somewhere in between the value that's in the fourth position. But I'm a little bit closer to the third, so I have to do some weighting, right? It kind of gets close to doing something similar to a weighted mean. So let's just work through a problem, and I think I can give you with some actual values, we can get a good idea of this, right? So let's say I have some returns on different metal funds. I arrange them from smallest to largest, and I want to find the 25th percentile, right? So the first thing I have to do, I've got them arranged from smallest to largest. Here I've got the position they're in. So I need to find what position would give me the 25th percentile. So the number of observations I have is 10. So I plug 10 into n. I want the 25th percentile, so P is going to be 25 here. If I compute this, I get 2.75. So that's not telling me the value of the 25th percentile. It's telling me that's the position of the 25th percentile. Well, it's not an integer, so I go up here. 2.75 is in between 2 and 3. But it's closer to which position? 3, right? So I look at the values in the second and third position. So I know that the 25th percentile will be somewhere in between these values, but it's going to be a little closer to 8 than it is to -7, or closer to 8.09 than it is to -7.34. But how much closer? Well, what we're going to do is essentially use whatever the decimal is. So here it's 0.75. We're going to use that to create some weights. So the sum of the weights we're going to use, we're only going to have 2 weights, right? We need to know how much do we weight the value in position 2, how much do we weight the value in position 3. We'll use this decimal to create our weights, and they'll always add up to 1. So 0.75 and 0.25. We said we're closer to the third position, so that's the value. We're going to weight a little bit more. So what we'll then do is take 0.75, multiply it by 8.09, add to it 0.25, right, the remaining thing that got us to 1, times the value that we're further from, so 0.25 times -7.34, add them up, and that should give us the value. It's called interpolating because we're not weighting each of those values in the second and third position the same. The one that we're a little closer to, we're going to weight more. Okay? Any questions on that? I know this is a little bit tricky. Maybe I just think it's a little bit tricky. So what if, we'll go to this in a second. What if I had, let's try this again today. Hopefully we don't have the same issues last class, but I think I figured out what that issue was. I'll go here. All right, so hopefully on Zoom, it looks like you guys are seeing what I want you to see, which is this. So what if instead I had something that looked like this? So let's say I got 2.3, all right? So I'm still in between that second and first position. And just a reminder, kind of what was on the slides. So we had what? -7.24 and 8.09, something like that. So if this was the position that the formula told me, let's see, someone probably. Why is 10? Oh, this might be an old question. So whoever, Mark, what 10 were you referring to? Oh, why is 10 the n? I see. So the formula was this, right? This n was the number of observations that we had. So if you look at the number of metal funds, it went from 1 all the way up to 10. So we had 10 metal funds. That's why the n was 10 there. That's a good question. So if whatever percentile we want, we plug it in and we end up with that 2.3 position. We still use that decimal to get our weights. So our weights would still be 0.3 and 0.7. All right. Oh, I left the chat bar in front of this. 0.3 and 0.7. But now when we look at the values, what position are we closer to? 2.3 is closer to the second position. So this is the value we want to weight. We're closer to the second position. So this is the value that we want to weight a little bit more. Okay? So we'll take that 0.7, that's our higher weight. Since we're closer to the second position at 2.3, we'll multiply the negative 7.24 by the 0.7, and we'll multiply the 0.3 by the value that our position is further from, which is a little bit further from 3 than it is to 2. Add those up, and that will give us the value that would be whatever percentile we chose here. I'm using 2.3. I don't know exactly what that corresponds to in terms of percentiles, but I'm showing you if it's a little bit trickier than the other one, because 0.75 was exactly what came after the integer in the previous one. So you knew that was the weight that you were going to multiply by the value you were closest to, right? But here at 2.3, you actually have to figure out what are my weights first, and then the one that gets weighted the highest is the position, the value in the position I'm closest to. See how it's a little bit different? Okay. And what if I had exactly, what if I got, the position was 2.5? Why is that easy? If I'm exactly smack dab in the middle of two positions, what is all I have to do? Each one's going to get multiplied by 0.5, which is really like getting multiplied by 1/2, which is really, if you added them up and divided by 2, would give you the same thing. So yeah, if you get a 0.5 as your position, it's really easy. You just find the average of the two values. Okay. Any other questions on that before we see the chat here? Okay. We're good? All right. So I have to go. I think I figured out why it didn't work last class. So I'll go back to my camera. Hit this. We'll hit this. There we go. Hopefully. Ta-da. Okay. All right. So we now know how to kind of find these percentiles. So something that's kind of, you might see in other classes that you'll use these percentiles for are called box and whisker plots. There we go. I was having a blank there. So what we'll do to make these box and whiskers plots is find the first, the second, and the third quartile, right? So the first, the second, and the third quartile, all that refers to is the 25th, the 50th, and the 75th percent. That 50th percent being the median, right? We said that we already kind of mentioned that. Once I have those, I'll compute something called that inner quartile range. The inner quartile range is take that third quartile and subtract, the first. Whatever that is, that's your inner quartile range. Okay? I'm then going to take that first quartile and subtract I'm going to subtract 1.5 times the inner quartile range, plot that point, and then I'm going to take the third quartile, add 1.5 times the inner quartile range to it to get my kind of upper point. And I'll show you an example of this in a second, but this is what we're going to do to build our box and whisker plot. So, and then this is called the QT test. So please don't reject me as an outlier because you are the Q test. Get it? Okay. Anyways, I thought that was a clever meme. So let's go here, and I'll kind of give you a visual of what this is going to look like. So what we're going to do, all right, is I'll just make up some values here for the sake of having something, right? So let's say quartile 1 is 50. My second quartile is 70. My third is, 85. Right? So what I'm going to do, I'm going to try to keep this all on the screen, is I'm going to plot my first quartile, my third quartile, make a box out of it, and then I'm going to plot here kind of where that median would be. Right? And it might not always look this equal. It might, like, sometimes the median might be really, really close to the third quartile and really far away from the first, or vice versa. What I'm then going to do is, okay, what was my interquartile range? Well, that was taking the third minus the first. So we'll go 85 minus 50, which is 35. So I'm then going to get my upper whisker, so to speak, right? I was going to take that third quartile, add to it 1.5 times my interquartile range. So that is 85 plus 1.5 times 35. All right, so that's what, 17.5, 40, 52.5. If I'm doing the math in my head correctly there, I might have made a mistake. 137.5. If I made a mistake, let me know. I'm trying to do this in my head, and I'm not always going to do everything in my head correctly. Right? That's right, though, right? 15, 17.5 would be 40, 52. I think, yeah. Okay. My brain's working a little bit today. And I would then create my lower whisker by doing the exact same thing, except I'm going to subtract 1 times the interquartile range from my first quartile, right? So I'm subtracting here. So what? 50 minus 1.5 times 35. So I actually would get negative 2.5, I think, there. Right. Any questions on kind of that process? Now, a lot of times you probably won't have to do this by hand. There's actually some options in Excel, I think, to create these. I'm not going to have you necessarily do it in this class, but I wouldn't be shocked if you end up seeing this in another class. And this is kind of tells you something about the distribution of the data pretty quickly. And the Q test there is if I have data that falls outside of those whiskers, I can reject that as an outlier, right? Or I can reject that from the data. I say, based on the Q test, this is an outlier in the data set. And so this is justification for when I'm creating these statistics, I'm actually going to ignore any values that are outside of that, right? So this is something that you might see pop up, especially if you're in some like upper level like research methods and research courses or something like that. I don't know, you might see this again. Okay? So I saw that question mark. So where am I getting 1.5? That's just the equation. So that's like something that was derived. We said, look, if we've got this range of data and something's 1.5 times even higher than, where we kind of see that third or first quartile, or lower than the first quartile, it's extreme enough, it's a unique enough value where we can reject it kind of from this data set. Right? We can say it's an outlier. So that's just something that's in the formula. All right, we'll switch back here. A little bit of time left. Just say, don't do this to me again. Okay. So that was, I think, actually all I had for us on these slides, but I had some additional ones that we'll go through here since we got a little bit of extra time and we lost a little bit of time last class. So, so we'll go through these slides still. So up to this point, we've really just primarily looked at one variable. A lot of times we want to know what's the relationship between two variables, okay? So to kind of set this up, we might want to know if one variable increases, what happens to the other? So it's kind of like the scatter plot we were talking about. If I see healthcare expenditures for a country go up, what happens to its life expectancy, right? So obviously, if one variable goes up, another variable can do one of three things. It can increase, decrease, or not change it really at all, right? So we have two measures of this relationship between two variables. One's called the covariance. The other one's we call it correlation or correlation coefficient, okay? So to find the correlation coefficient, we'll first need to talk about and how to find the covariance, all right? So we're gonna have two variables, X and Y, all right? And this is going to be our formula for that covariance, okay? We're going to go through, once again, try to read this formula, then go through some data and try to figure out how we do this. So we're going to take, we would have a data set with, say, healthcare expenditures and life expectancy. We've looked at that one before. I'm going to find the mean of both of those variables, okay? Once I have mean healthcare expenditure and mean life expectancy, I'm going to go to the first observation. I'm going to take whatever value it has for healthcare expenditures minus the mean healthcare expenditure. I'm then going to multiply that by whatever the difference is of that country's life expectancy minus the mean life expectancy that we had in that data set. I'm then going to do that for every single observation, or in this example, every single country in that data set. Once I'm done, I add all those products up, and then for the population, we divide by the total number of observations we had. For the sample, it's the exact same process, but we divide by n-1, just like for the variance. Covariance has, you know, similar kind of idea to the variance there. Okay? But it's a little bit different than the variance. Nothing's getting squared. So it does matter what side of the mean that these values we see are on. Okay? So I'll give you some data here real quick that we can kind of talk about. If we see this covariance be positive, that tells us that there's a positive relationship between x and y. As x goes up, y tends to go up as well. If we get a negative covariance, that means as x goes up, we tend to see y go down. And if we get a covariance as approximately 0, that's telling us as x goes up, y doesn't really change at all, right? So these are kind of the three ranges we can see. I think what we'll do is next class, since we really don't have a lot of time left here, we'll kind of walk through this data set. We know now that the covariance, if it's positive, it tells us there's a positive relationship, so on and so forth. We'll think a little bit more about why that's the case and a little bit about how the data, you know, results in this one statistic that tells us whether or not there's a positive relationship. Okay? So we'll talk a little bit more about this next class. So one thing I probably won't show you in class, just because we lost some time, but there's this Jon Stewart clip, and hopefully this link still works. If it doesn't, you should on YouTube just search Jon Stewart Anglo-Americans, I think. And it's about this economist who does all this work with what the wage premiums are, about like if you, better looking people we see in the data tend to get like better pay. And he kind of goes, it's pretty funny. He like compares it to like racial injustice. Like this guy's like crazy, but it's real. Jon Stewart does a great job of making it funny. And it kind of all stems from the very first thing we need to do to understand relationships between two variables like beauty and wages. The very first starting point are these correlation coefficients and these covariances. So we'll finish discussion of that on Monday, and then we'll jump in to some probability stuff. So I'm going to put up one of those Learn Smarts. You don't have to do it, but it's for Chapter 4. If you do want to kind of go through to get an idea about what we're going to be talking about starting next week, you can. Yeah.
I have a question about the connect assignment.
Yep.
Do we know enough now to take the assignment?
Yeah, you should have everything except for a little bit of the covariance stuff. Probably that would make a little more sense after Monday. But everything else we've worked through on that assignment. I think just the very last question might ask you to calculate a covariance or something along the way, and that will have to wait a little like till Monday. Yep. Any other questions before I let you guys out of here? We're good? Okay. I will see you guys next week. Have a good weekend. And just so everyone remembers, we have class on Labor Day, so this isn't a usual semester. So I'll see you guys Monday.